Yesterday we took a look at the Millikan oil drop experiment, which the purpose of it was to find the charge of the electron. Thomson found the charge to mass ratio of the electron, discovered the electron. That's a big deal. But didn't know what the charge was, didn't know what the mass was. So Millikan comes along, does an experiment, finds the charge of the electron, also finds the elementary charge, which happens to be the same as the charge of the electron, but also finds that charge is quantized, which means that you can have the elementary charge or a multiple of that, but not just any random amount of charge. Now, when Millikan performed his oil drop experiment, he ended up injecting these tiny little droplets of oil in between two charged parallel plates. Yesterday, I showed the top plate as being positive and the bottom plate as being negative. Today, I'm going to reverse that. Doesn't matter. Okay, I'm not trying to tell you that yesterday we were wrong or that yesterday we were right and today we're wrong. Okay, in the end, it doesn't matter which plate is positive, which plate is negative. We're going to have some positively charged oil droplets in between those plates, and we're going to have some negatively charged oil drops in between those plates. There's always going to be two forces acting on each of these oil drops. Now, yesterday, as is today, the force of gravity will be downwards on both of these particles, always. Always. No exceptions. And remember, they said yesterday the force of gravity is important now. It wasn't with the cathode ray tube because it was so small in relation to the electric force and the magnetic force, because it was just electrons in the cathode ray tube. Here, because we're dealing with oil drops that have significant mass, really, really light still, but significant compared to an electron, the force of gravity is important. There was also an electric force acting yesterday on both of them. Yesterday, the electric force on the negative was upwards. This time, the electric force on the positive is upwards, and the electric force on the negative is downwards, all because we switched the direction or the orientation of the plates. This is the one I want to focus on right now, and a very specific case of this. When these two forces are not balanced, this oil drop will accelerate either up or down, depending upon which way the net force acts. But when they are balanced, it's going to either be suspended, sit there right where it is, or it's going to travel up or down at a constant speed. That's what I want to focus on, when it's going up or down at a constant speed, or when it's suspended. In that case, we're going to say Fe equals Fg. We're going to say Q times E is equal to M times G. And we're going to end up solving for Q most likely. We get mg over E. That charge that you should find there should be either 1.6 times 10 to the minus 19 or a whole number multiple of 1.6 times 10 to the minus 19. Again, elementary charge, charge of the electron, charge is quantized. The first two questions that we had on 763 both relate to this situation, when the charged particle, the oil drop, was suspended or traveling at a constant speed. Was there any issue that we had with either of these two questions on 763? Perfect, Cole. Let's do number 2. Thank you. What's the electric field that will suspend an oil drop with this mass and a charge of plus 2e? It's not so difficult to do this question in terms of what's the value of the electric field, but the electric field's a vector, so it requires a direction as well. That's the more challenging part, and that's what I really want to show you here right now. We should draw a picture. Okay, we should always draw a picture for this. We've got an oil drop. Don't know whether it's, we do know that it's positive. Its charge is 3.2 times 10 to the minus 19 coulombs. We know if it's suspended that we've got to have a force of gravity acting down, and we're going to have an electric force acting up, because if they weren't opposing each other, then they couldn't balance each other. If the electric force on a positive particle is up, then the electric field has got to be which way? The positive particle experiences a force in the direction of the field, which means the electric field has got to be upwards. We've just answered the second part of the question there now. Which way is the field? Upwards. If it was a negative particle, it would experience a force opposite to the field. An upward force would mean a downward field. Positive particle, upward force, upward field. All right, let's find its value now. We're going to say Fe equals Fg only because it's suspended and these forces balance. We'll say QE is equal to mg, and we'll end up solving for E here, okay, which is not the norm. Okay, usually we solve for Q. Do the math there, mg over Q, and we end up getting 9.8 times 10 to the 5 newtons per coulomb. And again, we already established it's an upward field. Right? Cool, is that okay? Now, the other situation that we described was that second particle where the forces weren't balanced, or maybe even that first particle, but one force is bigger than the other. In the end, if we have a net force, an unbalanced force, we have to do what we did in Physics 20. F net is equal to the sum of the forces, Fe plus Fg. We're going to say Ma is equal to Qe plus m times g. And now's when we really got to pay attention to directions. Fg will always be negative. Okay, this will be positive or negative, depending upon whether it's up or down, and the picture will help you with that. Okay, and then again, acceleration will be positive or negative, depending upon which way it's accelerating, up or down. Let's take a look at question number 2 here. Okay, question number 2. I think if you can do question number 2, I think you're going to be fine with question number 1. Keeping in mind that, as we said yesterday, both of these answers are incorrect. Okay, they did both of these wrong. Number 2, find the acceleration of the sphere if the direction of the field is reversed. Let's draw a picture. Okay, that's what we do. We have a downward electric field. We have a particle that has a charge of negative 5e, or that's going to be negative 8.0 times 10 to the negative 19 coulombs. We know that we have a gravitational force downwards. Which way is my electric force? We have a negatively charged particle. There's a field downward. The negative experiences a force with or against the field. Against. So that means the field is going to be, the force is going to be upwards. Field is downward, force is upwards. All right. Let's say F net is equal to the sum of the forces. Let's say M times A is equal to mg plus QE. Cancel out a mass there? Appears on both sides, right? Can I cancel it out, Josh? No, because it doesn't appear in every term, right? Well, we got our mass here of 2 times 10 to the negative 14 times A equals 2 times 10 to the negative 14 times 9.81 plus 8 times 10 to the minus 19. Notice that I'm not plugging in the sign of the charge there. I told you guys this way back in Unit 2. Whenever you're plugging a charge into an equation, drop the sign of the charge. The electric field is 1 times 10 to the 5. Don't plug in the sign of the field either. Okay, notice it's Q times E with the absolute values around it. Don't plug in the sign of the field. Okay, what I want you to do at this point is now go back and look at the forces. Not the field, not the whatever, not the charge, but the forces. Gravity is downward, make it negative. Electric force, for my picture, is upward, make it positive. Solve for A. You get this number, combine them, divide by 2 times 10 to the negative 14, and I think we got negative 5.8. Was that right? So my acceleration would be 5.8 meters per second squared downward. I think for question number 1, the correct answer was 2 point something times 10 to the negative 13, wasn't it? 2.8 times 10 to the negative 13. Good. Any questions on either of those? Yeah. You know why you got the answer that they got for the first one? Because you made a mistake. You made the same mistake, actually, as they did, which is the electric field is upward. So you assumed when you did this that the electric force was upward. You assumed a positive force. But if you have a negative particle and the field was upward, force of gravity is, of course, going to be downwards, but the electric force would also be downwards. Does that make sense, Andy? Listen, if the people writing the book can make that mistake, Okay, it's an easy, easy mistake to make, right? And that's why I suggest to you guys that you draw the picture. That doesn't guarantee that you're going to get it right, even when you draw the picture. Your chances are much greater. Now, you may have done that. You may have drawn the picture. I'm not sure. But in the end, for all of you, okay, your chances of getting this right are much greater if you do draw that picture. All right, good, got it?